Hi friends, so in the previous video we saw the definition of a level set, and specifically we were interested in this zero level set here. So it's a higher dimensional function which has the variables x, y and t, and we saw that in our previous videos, like earlier videos, we saw that the curve can also be given by something like this, where the curve is given by c and it has of course the x and y variables, and then x and y are themselves a function of what we said as f theta and g theta. So now to include curve evolution in our uh, formulation, I am adding that x and y are also a function of t, because they would change as the time changes. So now x is f yeah, and parameterized by theta and t, and y is g of theta and t. And what we previously saw, that the unit tangent is given by the derivative along the arc length, which is given by cs here, or c theta by divided by the magnitude of c theta, or given by xs ys. So these definitions, they are still true even in level sets, because when we do this we basically hold our t as constant, and then x and y basically become functions of theta, and that way we have these definitions for the tangent and the normal. So these we have already talked about in our previous videos, and now what we are interested in doing is we want to see how the curve evolves when we are formulating it as a level sets formulation. So before we do that, we want to see if there are any other equations that we can have for these tangents and normals in level sets. So one thing which is special to level sets is along the curve we have that our level set phi is always 0. So what we can say is the derivative of the level set, which is given by phi s along the arc length, is also 0, because the level set itself is 0 along the arc length, so the derivative along the arc length is going to be 0. So we know that. So now can we use this to make some meaningful expressions? Let's see. So what we will have when we differentiate along the arc length is we will have phi of x, and then we will have x of s. Then we'll also have phi of y and y of s. And basically the t here is 0, so like it's a constant, so we don't have to consider that. Like right now we are considering it without time, so this itself is equal to 0, because t is a constant. Okay, so that's why that doesn't appear in our derivative, because that part of our equations is right now 0. So you could think of this as something like phi of x comma y, and then we are taking a derivative of that, so s of this. So t is not there because right now we are not changing time, it's a constant. So this is what we get, and as we just showed, that this is basically something like phi x comma y s, and this is excuse me, it's phi x comma phi y phi x comma phi y into dot product with xs comma ys, and that is given as 0, and we already know this is our tangent. So what that means is this has to be a normal, because the normal and tangents are orthogonal. So that's why we have that this can be given as del phi, or the spatial differentiation, and we have that is a normal. And to get the unit normal, what we'll have to do is the unit normal we'll have to normalize. So that would be given again by uh, basically phi x square plus phi y square, and that is del phi by the magnitude of del phi. So this is the unit normal of our in the level set perspective, and we also know the unit normal is given by ys comma minus xs. So I just want you to know that both the formulas are true, and it's not like just because we are in level sets the other one is no longer true. So both of them can be used, and in fact we will be using them when we derive the curvature in the level sets perspective. It will be a formula in terms of the phi function, and for that we'll actually be using the fact that there are two definitions of the normal. And so that's all for this video. In the next video I'll talk about how to finally get the curve evolution equation in level sets, because we haven't yet done that.